Hey there, here we go into the root test, or as I like to say, the root test. So the root test is actually a lot like the ratio test. It is not on the BC exam, but it is in a lot of BC classes, as well as in a lot of Calculus 2 classes in college. It's almost identical to the ratio test in that you're using it for fast functions, but specifically functions that are raised to an nth power, right? It's very particular. But the circumstances of it, right, the conditions are almost identical to the ratio test. Let me show you what I mean. If you're given a series, an infinite series, it will converge if the limit as n goes to infinity of the nth root of the absolute value of what you're taking the series of is less than 1, just like the ratio test, right? And the nth equals 1 to infinity, infinite series, diverges if the very same limit of the very same nth root is greater than 1. And then just like the ratio test, the test will fail if that same limit of that same root is equal to 1. Now, essentially what's happening here is when you have an nth root of something, you're taking that nth root of something, I should say, to kind of say what's the ratio as we go way, way, way far out. So this is perfect when you're raising things to the nth power. Again, I use the ratio test in these kinds of problems usually, but the nth root test the root test can come in handy. So when do we use it? When a sub n has terms, I shouldn't say has terms raised to the nth power. So again, not on that BC exam, but in a lot of BC classes and certainly a lot of Calc 2 classes in college. State whether the series converges or diverges, justify your answer. So again, to justify our answer, we will continue to list out any conditions that we need to. We just saw the conditions on the previous page. State the name of the test and whether we converge or diverge. So here notice that both the numerator and denominator are raised to the nth power. It's not a geometric series because we have that n in the denominator. So what I'm going to do is I'm going to take the limit as n goes to infinity of, and we'll take the nth root of the entire thing. So the nth root of e to the n over n3n. Now that is equal to the limit, and that's of the absolute value, of course, but that actually is a positive function the whole time through as we go to positive infinity. We get the limit as n goes to infinity of the nth root of, well, the nth root of e to the n, I guess we could simplify that down now. I don't need that nth root part. N divides into e to the n, right? The absolute value goes away. It's all positive. We just get e in the numerator. All over, you're dividing n into 3n. So you're saying, what times n gives me 3n essentially, and that would just be n cubed, something like that. And as we go to infinity, you get e over basically infinity cubed, which is equal to 0, which is less than 1. So our series, it's very easy to show actually if you're using this correctly, our series converges by the root test. So converges by the root test. Not bad. Not bad at all. All right, there we have it. Exclamation point, happy face. So what's happening here, if we expand this thing out, you'll see that you have e over n to the third plus e to the second over n to the sixth plus e, it's a pretty cool series actually, e to the third over n to the ninth plus dot, 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 until you get out to the nth term, e to the nth over n to the 3n plus dot, dot, dot. And we're basically saying this ratio right here, as we go to the nth power, acts like a converging geometric series. We're going to go to 0, right? That root, and that's less than 1, so it acts like a converging geo series. Just like ratio test, though. You can actually build it off of that, too. All right, here's another one. This is a perfect example, if I do say so myself. For the root test, you have stuff raised to the nth power. So we're going to take the limit as n goes to infinity of the nth root. So that'll be the nth root of this whole thing. So that'd be 5n plus 1 all over 3n minus 4, all raised to the nth power. The nth root of n is just whatever it is, and that's going to be the limit as n goes to infinity. What I mean by whatever it is, they cancel out, they undo each other, and you're left with 5n plus 1 all over 3n minus 4, and that's an easy limit to take. The 1 and the negative 4 don't matter as we go to infinity, only the higher powers do. 5n over 3n simplifies down to 5/3, which is greater than 1, so therefore this series diverges. So our series, or the series, we're going to take possession of it, our series diverges by the root test. Diverges by the root test. That's it. Not so bad, right? Not so bad at all, I don't think. Now, you also could have used the nth term divergence test here. The limit as n goes to infinity of this whole thing does not equal to 0, and therefore it diverges by the nth term divergence test. Okay, now on to the why behind this. Why does the root test make sense? Well, let's take a look at what I did here is I kind of looked at just a general, I don't know, any old series raised to the n, right? I took x to the n. And as we expand this thing out, what we realize is this thing particularly is acting like a geometric series, right? You're multiplying by x every single time. So by taking the nth root, we're basically peeling off that power to see what the ratio is between the terms. Because when you raise something to an nth power, you're repeatedly multiplying by that term by one more each time, or by more than that. So if we take the nth root of that, the absolute value of it, of course, we end up with just x, right? Especially if x is positive. So we end up with just plain old x, or the absolute value of x. And as long as that is less than 1, then it's a converging geometric series. If it's greater than 1, then we're diverging. And the reason why if it's equal to 1, then it's inconclusive is the same as with the ratio test. That's because there are certain series that if we use the nth root test, or the root test with, some will converge and some will diverge. So that's when you have, again, the result of 1. So if you're less than 1, then we know that we converge. I'll just put CONV. And if we're greater than 1, we diverge, just like in the ratio test, just like in the geometric series test. All right, that's it. And I didn't tell you at the beginning of this video, but this is the last series convergence divergence test that you are going to learn. Congratulations. See you in the exercises. Until then, though, be well and peace.